Welcome back, everyone. Now we're going to get into the nitty-gritty. So we spoke a little bit about elastic collisions and inelastic collisions before the break. Now let's investigate some of them, okay? So we know we're busy with conservation of kinetic energy. So now what we're going to do is we're going to go, what happens with kinetic energy during an elastic collision? So let's go and play, okay? So here's our simulation, and I'm not worrying about the momentum vector diagrams while we do this because I'm not really concerned about that. But what we're going to do is we're going to look at the values, okay? Now, I've got velocity here. And I've got mass, and what we're going to do is we're going to go back and forth between the two, between the black screen and this one, because we're actually going to do a calculation with this, because it's important for us to do that. So we're going to take note. Now, I know they're not moving at the moment, okay, because I haven't pressed play. But at the moment, we have my block A, the bluish one, number 1, which has a velocity of 1 to the right, which is my positive direction. So I'm going to take a note of that. And block 2 has a velocity of minus 0.5 because it's going in the opposite direction. And over here, I've put, so on this, actually, can I show the kinetic energy? There we go. I don't even have to do the calculations. Look at this. My total kinetic energy, that's what's in the bottom right-hand corner. So if we had to work it out, which we're not going to do now, I have 0.44 joules. So what they've done is they've taken the kinetic energy of block 1, which is a half mv squared, and they've added it to the kinetic energy of block 2. Remember, I said to you before the break, you cannot get a negative kinetic energy. That energy is very small, and I'm okay with that, because if we look at the velocities, they're not very big, and the mass isn't very big. So I'm not expecting a very big kinetic energy. So one thing to keep in the back of your minds is when you calculate the kinetic energy, look at the object, look at the size of its mass, and look at its velocity. And say to yourself, does it make sense that the kinetic energy is that big or that small? Unfortunately, I can't tell you that it's always going to be very big or it's always going to be very small. Depends on the objects. So let's let them collide. There we go. Oh, look at that. The total kinetic energy didn't change. It's elastic. I'm telling you it's elastic. I've also said to you earlier that this is very rare, so rare. The closest I can give you as an example for an elastic collision is a collision where, so something like snooker balls on a snooker table, because they're very hard, and the snooker table has a felt on it that gets rid of friction, okay? It makes it nice and smooth. But when those snooker balls hit each other, it's close to an elastic collision because of how hard they are, but it's not quite. In the real world, we don't get elastic collisions because whenever two objects hit each other, we hear a sound at the very least. Even if it's a tiny, soft sound, you will still hear something. Also, there's a heat transfer. Okay, because when they smack each other, we get heat transfer. Elastic collision, that doesn't happen. So let's just see if that's always the same. So let's reset this. Let's make the mass of my first object a bit bigger. Okay? I've made it 2. Look what happened to the total kinetic energy. It's now gone to 1,44. I've still got it as an elastic collision. Let's let them, oh, look at that. The 2 goes off with lots of energy. 1's going very slow now because 1 was very big. The momentum, the total momentum stayed the same, and the total kinetic energy stayed the same. So before the collision, we had a total kinetic energy. After the collision, we have a total kinetic energy, and it remains constant. Let's look at what happens. Let's make the initial velocity of this object 0. In other words, now we're going to see still an elastic collision, and watch what happens. Total is still 1,25. Did you see that? Look at the total. It's 1,25. All the kinetic energy in the system's coming from number 1. Number 2 has no kinetic energy because it's stationary. When it hits number 2, some of the kinetic energy from number 1 gets transferred to number 2. Number 1 keeps going, but my total is still 1,25. Number 1 goes slower because of the collision, and number 2 speeds up, but they still go. Let's see what happens. Let's make number 2 the same mass as number 1, but now it's stationary. Okay, my total is still 1,25. Let's see what happens. Number 1 stopped. Same mass. Okay, if you go and look at a thing called a Newton's cradle, it's a good thing to look up online. It's those toys with the 5 little balls, and they swing backwards and forwards. Okay, those are close to elastic collisions. It's this concept that because the metal balls have the same mass, they can transfer all their velocity to the next one, so they go backwards and forwards like this. But you hear a sound, so eventually they slow down because their kinetic energy is getting transferred to sound, so it loses it. And there's air resistance. We're ignoring air resistance, okay? This is a completely isolated system. We're ignoring air resistance, okay? And I could do this all day, but we're not going to. So when we look here, so for elastic collisions, my total kinetic energy before they collide has to be equal to the kinetic energy after. When we do calculations, this is something I have to prove. We do not start with that statement. So that means we have to go the sum of the kinetic energy before will be equal to a half mass of the first one times its initial velocity squared plus a half mass of the second one initial velocity squared. Okay? We have to do that calculation first and separately. Then we can do the calculation for, there should be an E there, after. And that would be with my final velocity, with my final velocity of number 2. And then once I've got those two values, I can compare them. All right? And only when I compare them can I say they're equal or not, and then say it's an elastic collision. Please, this is very important because you often just going to start with they're equal, and then the maths goes out the door and something goes very wrong, so we're not going to worry about that. Now, let's look at an inelastic collision. So now we're going to go back here. Let's reset this. We're back at what we had here. Now I'm going to change whether it's elastic or inelastic, okay? Now, if you look at my little scale over here, no, stop it, over here, I can go to 100% inelastic. Okay, we're not going to, no collision is 100% inelastic. So I'm going to make it a percentage. It doesn't actually matter. I have my two objects. They're going at the one stationary, one's moving. Remember, when this was elastic, number 1 stopped and number 2 kept going. So let's see what happens if I put them together now. Oh, now that's more realistic. Okay, watch again. We've made it an inelastic collision. They keep, number one keeps moving now. When it was elastic, number one stopped. Okay, now it keeps moving, which is more likely going to happen. Let's look at the kinetic energy. Before they collide, it's 1,25, the total. After they collide, it's now 0,68. The kinetic energy got smaller. In reality, if we could hear this, the difference in the kinetic energy, the fact that it got smaller, is sound. You would hear them colliding, okay? There's going to be friction between them, so you'll have heat. If these were metal balls, you might see light, okay, because they're rubbing against each other. Let's see if that's always the case. So, let's make number 1 kilogram, okay. Let's make number 2 moving in, say, the same direction as number 1, and it's going at 1. So they have the same velocity, and let's see what happens when they collide. My total kinetic energy is 1,75, so let's see. Oh, they're not going to collide. Why won't the balls collide? Well, they're going at the same velocity. One's never going to catch up. So let's reset it, okay? Let's make it, so let's make number 2 go slower. Let's make it 0.5, okay? And let's give 1 a bit of a fighting chance. So I'm going to put 2 a little bit further, closer to 1, all right? And there's more space for it to try and catch up. Total kinetic energy, 0,81 joules. Let's see what happens. There we go. They collide, but 0,73, so we lost energy again, and they move on. Now, with all the ones we've done so far, we've had them end up going in the same direction. But what happens if they change direction? Okay, so let's reset, and I'm going to do this, and let's change that one to be going at minus 0.5. Okay, let's see if it bounces. We got 0,81 kilojoules, so here we go. It doesn't matter that it changed direction. But can you see that by changing direction, we had a much bigger loss in kinetic energy? So here, the original was 0,81. When they collide, they have a much bigger, now becomes 0,08. So in other words, when two objects collide with each other and they go in opposite directions, more kinetic energy is lost. There's a bigger transfer of kinetic energy, okay? And that's always the case. So let's go here. So when we have an inelastic collision, this is the concept. Kinetic energy before is not equal to the sum of the kinetic energy after. Now here we need to be careful. Most of the time, the kinetic energy before will be smaller than the kinetic energy after. It's not always the case, so I can't say bigger than or equal than. They're not equal. Just like with an elastic collision, in order to prove this, I have to work out the total before and the total after, and then compare them. Okay, we can't start with the statement. Very, very, very important. That, okay, brings us, oopsie, to the end of this part, okay? Lots to think about. In the next part of the program, we're going to do some calculations. So take a short break, and I'll see you in a couple of minutes.